Hello students, let us discuss our next topic, that is moment of inertia. Again, I'm taking the screenshots of NCERT and all the material I'm taking from NCERT. So let us discuss what is moment of inertia. We have already mentioned that we are developing a study of rotational motion parallel to the study of translational motion with which we are familiar. We have yet to answer one major question in this connection. What is the analog of mass in rotational motion? So basically what we are doing in this chapter, we are finding the physical quantities which are analog in the translational motions. So like what we have discussed, torque, that is the analog of the force. Angular velocity, analog of velocity, right? Now next our question is, what is the analog of mass in rotational motion? Like the physical quantity which we are using in translational motion, which is mass. So what we are going to use in place of mass in rotational motion? We shall attempt to answer this question in this present section. To keep the discussion simple, let us consider rotation about a fixed axis only. Let us try to get an expression for the kinetic energy of rotating body. So we are going to find out the expression from the expression of moment of inertia from kinetic energy of a rotating body. So here what we are going to consider, we'll consider the rotational motion of a body about a fixed axis, and we are going to find out the kinetic energy of that body. We know that the body rotating about a fixed axis, each particle of the body moves in a circle with linear velocity, which is given as Vi is equal to R omega. So whenever the object is moving in a circular track, we know that the linear velocity at any time can be written as R into omega, where omega is the angular velocity. So here we are going to consider any arbitrary body, a rigid body, and let us consider this is the axis of rotation. And now let us consider the body is rotating about this fixed axis of rotation. You see, when the body is rotating, the different particles, they are moving in circles. If you are going to concentrate only one particle, for example, the particle is here, it is going to move in a circular track of radius r or Ri, if I am talking about ith particle. So R is what? R is the radius of the circle on which ith particle of the body is moving. So linear velocity of ith particle can be written as Vi is equal to Ri into omega, where omega is the angular velocity of all the particles. The kinetic energy of this particle is, kinetic energy, we know that this is half mv square. So we want to write it for ith particle. So we can write kinetic energy of the ith particle is half mi Vi square. Now we are going to substitute the value of Vi from here. So it would be half mi Ri square omega square. So mi is the mass of the ith particle. And if you want to find out the total kinetic energy of the body, so what you are going to do, you will find out the sum of kinetic energies of all the n particles. So we are taking summation which is varying from 1 to nth particle. So you can write the expression of the kinetic energy of the ith particle. So here what is n? N is the number of the particles in the body. And one very important thing, as you see, when this body is rotating, this omega would remain constant for all the particles. So that is why we are writing this out of the summation. So we have got something here in the bracket, that is summation I varying from 1 to n mi Ri square. Now one very important expression we have got for the kinetic energy. This is half omega square into something. And you see, in translational motion, it is half mv square. So this was the kinetic energy in the translational motion. So v has been replaced by omega here. So m, it means, is replaced by this expression. So we can conclude the expression I'm circling here is the rotational analog of mass. So here we are going to define a new parameter characterizing the rigid body called moment of inertia, I. And it is given by this expression, summation I varying from 1 to n mi ri square. So this new variable we have obtained from the expression of the rotational kinetic energy of the body. This is the rotational analog of mass and it is called moment of inertia. So if you want to find out the moment of inertia of any object whose mass particles are given and for which you know the radii of the circles in which the different particles are moving, you have to simply take the summation of this physical quantity mr square for all the particles. So with this definition, the kinetic energy, rotational kinetic energy can be written like half I omega square, where I is rotational analog of mass, omega is rotational analog of velocity. So one very important expression we have obtained from the moment of inertia, that is summation I varying from 1 to n mi ri square. The parameter moment of inertia I is the desired rotational analog of the mass in linear motion. In rotation about the fixed axis, the moment of inertia plays a similar role as mass does in linear motion. So mass in linear motion and moment of inertia in rotational motion, they are going to play the same roles. Now moment of inertia of a ring, if you want to find out, let us try to find out the moment of inertia of a ring. Consider a thin ring of radius r and of mass capital M, rotating in its own plane around its center with angular velocity omega. So here we are going to consider a thin ring and it is rotating in its own plane about an axis which is passing through its own center and moves with the speed r omega. You see, if the ring is rotating like this about this axis which I have drawn here, and each mass particle is moving with the velocity v, which is equal to r omega, because r is the radius of the ring. Now if you will substitute v here as r omega, you will get this expression. Omega is angular velocity. So we have got one new thing here which is equal to the rotational analog of mass, that is mr square. So I should write r square here. So I here is mr square. So this is what? This is a moment of inertia of a ring, that is mr square. Now the factors on which moment of inertia depends. As you know that in translational motion, mass will remain constant. It is not going to change. Whether the mass is going along x-axis, y-axis, z-axis, it would remain constant. But this is not the case with the moment of inertia. So let us see. As the mass of the body resists a change in its state of linear motion, it is a measure of its inertia in linear motion. So we already know that inertia is what? This is the resistance of a body to change its state from rest or motion. So the mass is a measure of the inertia in linear motion. Similarly, moment of inertia about a given axis of rotation resists change in its rotational motion. So if a body is at rest and you want to put that body in rotational motion, then immediately you are not able to do so because of the resistance which the body is opposing. So when it is going to resist any change in its rotational motion, that is because of moment of inertia. It can be regarded as measure of rotational inertia of the body. It is a measure of the way in which different parts of the body are distributed at different distances from the axis. Unlike the mass of the body, moment of inertia is not a fixed quantity. Very important thing. Moment of inertia is not fixed quantity, but it depends upon the distribution of mass about the axis of rotation and the orientation and position. One is orientation and position of the axis of rotation with respect to the body as a whole. So three things we have discussed, we have seen here on which the moment of inertia will depend. Distribution of mass about the axis. For example, if I am having a metal and I am making a solid sphere, or I am making a hollow sphere from the same metal, or I am making a ring, or I am making a rod. Mass, if you see, if the amount of the metal or quantity of the metal is remaining constant, mass of all these objects I am making would remain constant. But the moment of inertia would be different. If I am making solid sphere, moment of inertia would be different. If I am making hollow sphere, or I am making disc, or I am making ring or a rod, moment of inertia would depend how the mass is distributed. Second thing is orientation and position of the axis of rotation with respect to the body as a whole. Secondly, it depends upon the orientation and position of the axis of rotation. If you see the axis of rotation is changed, let us consider a cylinder. Here I am drawing the cylinder. Now you see, if the axis of rotation is this, it would have different moment of inertia. But if this is the axis of rotation, moment of inertia would be different. So moment of inertia would depend upon the orientation and position of the axis of rotation. As a measure of the way in which the mass of a rotating rigid body is distributed with respect to the axis of rotation, we can define a new parameter, the radius of gyration. It is related to the moment of inertia and the total mass of the body. So one more physical quantity we are going to define, that is the radius of gyration. What is that? Radius of gyration. Let us define the radius of gyration of a body about an axis may be defined as the distance from the axis of a mass point whose mass is equal to the mass of the whole body and whose moment of inertia is equal to the moment of inertia of the body about the axis. So let us consider one body I am having here, and let us consider this is the axis of rotation. If I say the moment of inertia, I know this moment of inertia is I, that is m1. If I say all the particles are having the same mass, so I can write mr1 square, mr2 square, and so on till mrn square. Now if I consider a point here, so the distance of this point from the axis of rotation, so that this point is having the mass as that of the whole body, and if whole of the mass is situated here, and the moment of inertia, if I'm going to calculate for this point mass, that moment of inertia has to be equal to the moment of inertia of the whole body about this axis. So this distance would be known as radius of gyration. So what I am doing here, I have considered that whole of the mass is situated here. So what would be the moment of inertia if I am finding the actual distribution of masses about this body? This would be mr1 square mr2 square till mrn square. And if I am considering whole of the mass to be here and it is at a distance k from the same axis of rotation, what would be the moment of inertia? That would be mk square. So if you will equate, so what I have done here, I have divided and multiplied with n, and this would be equal to mk square. So this m into n is basically capital M. So equating both of these equations, k square is equal to r1 square plus r2 square till rn square divided by n. So this is the expression of the radius of gyration. So radius of gyration, so it is basically mk square, where k has the dimensions of length. The length k is a geometric property of the body and axis of rotation. It is called the radius of gyration. The dimensions of moment of inertia are ml square and SI units are kilogram meter square. So in this way you can find out and define the radius of gyration. So that's all for this lecture. Thank you.